Okay, so we have three equations. The first two are the first two equations of stellar structure, and then we've introduced the equation of state in the last lecture. This isn't classed as an equation of stellar structure, but that's just naming. These are three equations. Remember, we started off with three unknowns. We actually have five now because the equation of state brought in temperature and mean molecular mass. So we don't have enough equations to solve everything uniquely, but we have enough to start looking for some valuable physical insights into the properties of stars. And in this lecture, we're going to derive some approximations, some useful relations, and some useful order of magnitude estimates of quantities that will give us a good deal of information about how stars work and what the conditions are like in the interior of stars. So let me start off with the approximation that we've already encountered involving the equation of mass conservation, where as an order of magnitude estimate, what we can do is replace the density with the average density in the star, which is a constant. And then we can integrate this equation to get the total mass of the star. When we integrate 4 pi r squared, we get 4/3 pi r cubed, and putting in the limits, we get big R cubed, where R is the radius of the star. And this is multiplied by the average density. Okay, so in other words, the average density, you can either represent the average density by saying rho average or rho bar. It doesn't matter. I seem to have started doing both, which is a little overkill. Let me go back to just doing rho average, just to keep the notation simplified. So the average density is just the total mass divided by the total volume of the star. So this is what you would intuitively expect to calculate for the average density. Okay, now we can use this approximation to also integrate the equation of hydrostatic equilibrium. Okay, so if we multiply both sides by dr here and integrate, we have the integral of dp is equal to minus g, which is a constant, times the integral of the mass inside radius r, density inside radius r, over r squared dr. Okay, what are the limits of integration? Well, we're going from the center of the star, r equals 0, to the surface, little r equals big R. At the center of the star, the pressure is going to be some value, let's call it PC for central pressure. And at the surface of the star, the definition of the surface of the star is when the pressure drops to 0. Okay, so this side we can integrate immediately. dP integrates to p, putting in the limits, we get minus pc. Over on this side, to integrate this, we either have to know how mass and density vary with radius, what this mass as a function of radius and density as a function of radius is, or we need to make some estimate or approximation. So we're going to replace rho by the average value of rho, and we're going to replace the mass inside radius r with the equivalent equation to this. So we saw that this comes from the fact that the mass inside radius r is equal to, approximating rho to be a constant, 4/3 pi little r cubed rho average. So inserting this into here and replacing this rho with rho average and pulling the constants out, we get minus g times 4 pi over 3 times the integral of 0 to r. We're left with an r cubed here times rho average. We're left with another rho average from that, and we're dividing by r squared. Pulling the rho average, the constant rho averages out, we get 4/3 pi rho average squared on the outside, and then the integral from 0 to r of r cubed over r squared is r dr. Okay, so integrating r, that integrates to r squared divided by 2. So we get 4/3 pi rho average squared times big R squared over 2, which is what this integral ends up being. Now, 4/3 pi rho average is just the mass over the radius cubed from this equation up here. So this is equal to minus gm rho average divided by r cubed times r squared over 2. And we should put an approximate sign in all of this, since we are approximating rho as rho average. And then this r squared cancels with 2 of those r's, and we're left with PC is approximately gm rho average divided by 2r. And with this approximation, I should point out there are other ways of approximating this, and the textbook derives an expression in a slightly different way, but you still get something of the same order of magnitude. So all of these estimates give you the same order of magnitude for the central pressure. Having derived that, we can plug this in the ideal gas equation, and we can get an estimate for the central temperature of the star. So let's do that. This ideal gas equation of state implies that the central pressure is equal to some estimate for the density, rho average, divided by the average molecular mass times mH, divided by Kb times the central temperature. And so if we combine these two and solve for Tc, then we find that Tc is about gm mu bar, or I'm sorry, mu average, mH over 2 kb times the radius of the star. And when estimating this, we can assume to a good approximation that the sun comprises a gas of, or a plasma of hydrogen, ionized hydrogen, therefore mu average is about 1/2. So this allows us to derive estimates for the central temperature of the star as well as the central pressure. Plugging in numbers for the mass of the sun and the radius of the sun allows us to evaluate these things, and as homework you will be evaluating some of these quantities. Okay, another thing that we can do, another interesting quantity to derive, is the so-called dynamical timescale of the sun. And this is an estimate of how long it takes the sun to readjust to large-scale changes in its interior. So, for example, if for some mysterious reason the pressure inside the star suddenly doubled, how long does it take the star to adjust to re-equilibrize, if that is a word, which it isn't? And you can derive an order of magnitude estimate for the dynamical timescale by calculating the so-called freefall timescale of the sun, or a star. So what this means is, you imagine if this is the star, the question simply is, if you were to suddenly click your fingers and remove all the internal pressure in the star, how long would it take matter at the surface of the star to free fall into the center of the star? In other words, to fall through a distance r under an acceleration due to gravity, which can be given approximately as gm over r squared, where m is the mass of the star and r is the radius of the star. Well, if this matter starts from rest, zero velocity, then the time taken for it to fall into the center of the star is going to be given by the fact that the distance is 1/2 gt squared. This is just one of the classic kinematic equations, where t is the time taken to fall from here to here under the acceleration g. Rearranging this, we get an estimate for the dynamical time scale. So here t I'm replacing with tau dynamical as 2r over g square rooted, which is substituting in for g, big Gm over r squared. This is 2r cubed over gm to the half. And again, I'll leave it as an exercise to estimate what this quantity is in the case for the sun. finally, what we can do is something that proves quite insightful is to figure out what are the plausible sources for the sun's energy. We know what the sun's luminosity is. We can measure that directly, and it is 4 times 10 to the 26 watts. And remember, a watt is a joule per second, the amount of energy radiated by the sun per second, or the amount of energy being lost by the sun per second. Whenever we write down quantities relating to the sun, we indicate that by the subscript circle with a dot in the middle. So if we think up a mechanism by which the sun gets this energy that it's radiating away, and suppose we then can calculate, based on that mechanism, the total energy stored inside the sun in joules, so let's call that big U, then the time taken to radiate away all of the sun's store of energy is just going to be given to the total energy divided by the rate at which it is radiated away. So if we can figure out this quantity for a given mechanism, we can estimate the time scale over which the sun loses all of its energy. So let's go through an example of doing this. One of the earliest proposed mechanisms for the energy source of the sun came from Lord Rayleigh, and he postulated that the sun gets its energy from gravitational potential energy. Basically, the sun is slowly over time contracting, and whenever something contracts, it releases gravitational potential energy, right? Just like when I drop an object, it gets closer to the center of the Earth, it releases gravitational potential energy, which gets turned into kinetic energy and then heat and sound energy, which gets radiated away. So Lord Rayleigh said maybe the sun is powered just by the slow gradual contraction. So let's see if this is a plausible source of energy for the sun. Well, we've derived an estimate for the total gravitational potential energy of the sun. It was minus 3/5 gm squared divided by r. And so the gravitational energy time scale, let's call it tau grav, is just equal to this quantity divided by the luminosity of the sun. So let's estimate how much energy this is. What is the gravitational potential energy of the sun, roughly? Well, we're just interested in the magnitude, so the minus sign we can neglect. Big G, Newton's gravitational constant, is 6.7 times 10 to the negative 11 Newton meter squared per kilogram squared. The mass of the sun, m, is 2 times 10 to the 30 kilograms, and we need to square this. And the radius of the sun is about 7 times 10 to the 8 meters. So that's 700,000 kilometers, roughly 400,000 miles. Okay, so we're doing order of magnitude estimates. In order of magnitude estimates, the basic rule is if you can't do it in your head, then you're not doing an order of magnitude estimate. So, for example, here 6.7 and 7 are roughly equal, so they roughly cancel. 10 to the negative 11 divided by 10 to the 8 is 10 to the negative 19. 2 times 10 to the 30 squared is 4 times 10 to the 60. Okay. 3 fours are 12. 12 divided by 5 is roughly 2. Again, 2 within an order of magnitude. 10 to the minus 19 times 10 to the 60 is 10 to the 41. So roughly, to within an order of magnitude, the gravitational potential energy is 2 times 10 to the 41 joules. So that means that the gravitational energy time scale is 2 times 10 to the 41 divided by 4 times 10 to the 26, and that's 5 times 10 to the 14 seconds. Well, there's about 3 times 10 to the 7 seconds in a year, so this is about, again, to within an order of magnitude, it's 10 to the 7 years. Okay? So that's 10 million years. That's how long it would take the sun to lose all of its gravitational potential energy, if that were the source of its energy. Now, the age of the Earth, we know pretty well. It's about 4.5 billion years times 10 to the 9 years. This is about 500 times bigger than this. Okay, so this immediately is a big problem for this idea. It seems very unlikely that the sun could be powered by gravitational potential energy, because if it was, then the Earth would have existed for 500 times as long as the sun. So we can rule out this energy mechanism. Note that, again, the order of magnitude estimate is all we needed to do, right? It doesn't matter whether this is 2 times 10 to the 7, or 4 times 10 to the 7, or 3.7 times 10 to the 7, or 5.2 times 10 to the 7. It is still 100 times bigger than this, which rules it out. Okay, some other order of magnitude estimates for timescales. Some other possibilities are that the source of energy is just thermal energy. So in other words, the sun was born hot and it's just been cooling off. There's no energy is being produced inside the star. It is just cooling over time as it radiates away those 4 times 10 to the 26 joules every second. So let's examine whether that is a plausible mechanism for the source of the sun's energy. So it's going to turn out, and we'll derive this next week, that there is a theorem called the virial theorem that says that the thermal energy of the star is the same order of magnitude as the gravitational potential energy of the star. Given that we've already calculated the gravitational potential energy of the star, it should be fairly trivial for you to calculate the thermal energy timescale and comment on whether thermal energy is a plausible mechanism. The next possibility, and as we'll see, this is one of the ideas that students often have, is that the sun is powered by chemical combustion. The sun is literally a ball of fire. Right? So this is a chemical source of energy. And to estimate whether that is plausible, we can just take the most efficient combustion reaction that we know of, which is the combustion of hydrogen. When you combust hydrogen, you release 141.9 kilojoules per gram of substance that you are combusting. So in this case, the total chemical energy inside the star is just the mass of the sun times 141.9 kilojoules per gram, and you need to be careful to convert grams into kilograms and kilojoules into joules in order to get the right answer. So it'll be an exercise for you to calculate this and then calculate the chemical burning timescale for the sun, and again comment on whether that is a plausible energy source for the sun. The final source of energy is nuclear. It could come from nuclear reactions. And in that case, we need to know the energy released for nuclear processes. And again, the most efficient nuclear process is the fusion of 2 hydrogen nuclei into a helium nucleus. And that releases of order 10 mega electron volts of energy for every atom of hydrogen that gets combusted, or not combusted, sorry, that undergoes the nuclear reaction. So from this, you can derive the nuclear energy timescale and comment on its plausibility. Okay. Again, I will leave this as an exercise for you to extract U nuclear from this information and calculate tau nuclear.